First of all, a huge thanks to everyone. I am very happy to be here today. And for all of those who don't know me yet, my name is Alice Molemi Ore, and I am a first year PhD student at the University of Kassel. So today I am presenting my student research abstract called the Continuous Time Generative Graph Neural Network for Attributed Dynamic Graphs. And before we go into more detail about the GNN model and my research approach, I'm going to fix some important terms and concepts used in this presentation, giving an introducing example. So a graph neural network, or in short a GNN, is generally just like an ordinary artificial neural network, with the difference that it uses graph data as input. And to understand what GNNs benefit from and how they are superior to artificial neural networks, we first have to look at what graphs are in the first place. Formally spoken, a graph is nothing but a set of nodes and a set of edges that encode some relation between the nodes. And with this simple object now, we can already try to model real-world problems coming from social networks, citation networks, or electrical networks, like, for example, wind turbines connected by the power grid wind network. And as real-world problems usually are, they come with much additional information that can be encoded, for example, into the node's attributes. And the content can be anything relevant to the problem, such as the location, the nominal power, the wind direction, and so on. And similarly, of course, also edges can be attributed in the same way. But still, this seems to be a quite simple model. We must equip the models with some time-dependent changes to make the models far more realistic. So here in this example, one can see that both node and edge attributes are changing with time. And especially for our example here, it makes sense to include dynamics just because wind turbines depend on the weather, which is already a dynamic system. So now the question is, what problems does this type of modeling cause? So most of the graph neural networks are not capable of handling such complex graph models. In fact, a large part of the models can only process static, or in other words, time-independent graphs. The few GNN models that can handle attribute dynamic graphs expect a very special graph representation, which brings us to the following question. How do we represent a dynamic graph? The most commonly used representation is the so-called discrete-time representation, which, given an axis of time steps, is nothing but a sequence of complete graph snapshots. At this point, I also want to emphasize that the snapshots are not time-stamped, so we just know the order of the graph snapshots. Opposed to that, there is also the continuous time representation, which just keeps an initial static graph snapshot from a start time t0 and exchanges all other snapshots with time-stamped event tuples encoding the dynamical behavior of the graph. So we end up with a set containing the initial graph and a set of time-stamped events. Now the next question is what we want to do with all this and what our GNN model should be able to do. So first of all, the GNN should be able to handle attribute dynamic graphs. And this is because it has already been shown that nearly any real-world problem can be modeled as an attribute dynamic graph. Another benefit of our model is that existing graph models can be extended by including changing attributes, leading to more accurate results. And if the attributes encode multiple information, for example, in a vector, those are learned simultaneously. Furthermore, our model should be able to predict attributes. Using the continuous time representation also comes with some advantages. That is, the GNN can again lead to more accurate results if we incorporate real-time values. And besides that, it makes the GNN updatable with every new incoming event and thus prevents retraining from scratch. And on top of that, we even save some storage as we don't need to save many huge graph snapshots. Another aspect that is nice to have is if the GNN model is generative. One reason for this is that there are not enough dynamic graph datasets that contain all possible dynamics. One of the reasons is that there was no graph neural network that could work, for example, on attribute dynamic graphs in continuous time. So those dynamic graph datasets are still missing. To briefly touch on another point, a positive side effect of dynamic graph generation is that it motivates the development of new graph neural networks for new graph learning problems, such as dynamic graph classification, which could be used, for example, in drug discovery. So how do we best go about making our wishes? Or what is the GNN approach? As you can see, the GNN approach can be easily divided into 4 parts. So let's say we have an attributed dynamic graph in continuous time representation. Then the first step would be to take the initial graph and squash all the events together up to the next timestamps and work with the resulting graph snapshot for each of the timestamps. Having this on each of the graph snapshots, we can now perform, for example, a node embedding as shown on the upper side of the figure using an arbitrary but suitable so-called variational autoencoder that in our case is a graph neural network that learns the distribution of embedding coordinates of the node's attributes. And to illustrate that, in the bottom part of the figure, the node embedding coordinates correspond to the mean value, and the circles around stand for the learned variance of the node attributes embeddings. To incorporate real-time values now, we can interpret time as a new embedding space scaling axis. So practically, as illustrated in the figure, we tear the embeddings apart by timestamping them. And in the last step, focusing on each node and its embedding in time, for example, node n in the figure, we can learn a Gaussian regression for each node and simulate the node attributes dynamical behavior. In this sense, the function fn corresponds to the mean of the distribution resulting from the Gaussian regression. And the gray area stands for the uncertainty coming from the learned variance. So now, how can we conclude and what are the further future work challenges? First of all, our GNN can handle attribute dynamics in continuous time, which up to now was still an open problem. Using the variational autoencoder, we learn the distribution of the node's attributes embedding coordinates for each timestamp. And the Gaussian regression in the embedding space leads to a distribution of the node's attributes dynamical behavior. Applying the decoder on new forecasted embedding coordinates of a node leads to an attribute forecast of the same node. The predictions can be made using inter and also extrapolation and take prevailing uncertainties into account. Taking whole functions that are similar to the Gaussian regression functions and applying the decoder of the variational autoencoder on a sample of points within some time range leads to new dynamic graph datasets. And as a last closing point, the whole approach can be extended to so-called structured dynamic graphs that change in their amount of nodes and edges using an additional pre-processing module, as for example, the one that will be introduced in the following talk. Thank you very much for your attention. And now I am open to answer some questions.